I am sorry. Here, first part overlapped with my presentation for summer school in the first 2 days. And here I present this tunnel structure Josephson junction and a lot of version of, for example, superconductor constriction and superconductor type of Josephson junction, SNS junction, and superconductor ferromagnetic superconductor Josephson junction. And this one, here also I present new result related with observation of Josephson effect in Bose-Einstein condensation in cesium atoms. This one, Fizrev letter, 2005 years. And here also for young people, I present fundamental relation in Josephson junctions. This one, stationary Josephson junction and non-stationary Josephson junction, and here Shapiro's case, and also general equation for the study of dynamics of Josephson junctions. And our aim here to take into account other parameters symmetry and multi-component character of Josephson of superconducting state on current supercurrent relation, on Josephson current relation. Here also for young people are present structure of superconductor of the parameter in PCAs, in compressed superconductors. In compressed superconductors we have, as you know, D-wave character of other parameters, and in the 2002 years was discovered two-band electron phonon based MgB2 superconductors, and in 2008 years it was discovered ferron based superconductors, and these superconductors seems, these two class seems many band superconductors. This one MgB2 is two-band superconductor, and this one in the case of different compounds, or ferron based compounds, there are sometimes possible three-band, or sometimes possible four-band calculations in study of superconducting state in these compounds. And here in study of properties of Josephson junction in such systems, for example, in the case of single band, two-band case, and in the case of single band, two-band, three-band Josephson junctions. In this case, we should take into account two-channel character of Josephson current because of, as you can see here, it is one difference of phase in Josephson junction, and here we have phi. This phi related by the epsilon parameter. This one epsilon parameter, it means free energy functional, Ginzburg-Landau functional interband interaction parameter. If epsilon is positive, then we have opposite character of this two-channel current, and in the case if epsilon negative, in this case we have in the same direction Josephson current, and here total critical current is the sum of two critical currents. In the case of three-band superconductors, here also in the case of three identical Josephson coupling between other parameters, here we have 2 pi over 3 and 2 pi over minus 2 over 2 pi over 3 phase difference, and also in this case we have three Josephson current. And here in our study we will use general expression for the calculation of effective critical current of in such systems. And here I also present equation related with calculation of critical current in the case of derive superconductors, and here result of Sigrist rise. As you can see here, final result is determined by the angles theta L and theta R. This one derive here taking into account derive character of other parameters, and as you can see here, theta L is the angle between plane of junction and derive parameter. And similar calculation also was conducted by Tanaka using green function methods. And in general case, we have sine phi and cosine phi terms in supercurrent. And here also calculation is the case two-band superconductor here in Amilanchuk, and also shown changing of current phase relation in the case of two-band superconductors. And here experimental results by Bauch, and here experimental results related with ratio of second sine to phi term to amplitude of first, this one, sinus phi. And as you can see, at low temperatures, it was evidence of increasing of amplitude of second term. It means that in study of characteristic of qubits based on Josephson junctions with unconventional with anharmonic current phase relation, we should take into account such effects. And here I also present some calculations, standard calculations in the case of Josephson dynamics, taking into account this one is equivalent scheme of Josephson junction, and here shunt resistor and shunt inductor. And here I present some result related with calculation of effective critical current, inclusion of second harmonic, this one sinus to phi, and inclusion of fractional also term into current phase relation leads to changing of effective critical current. And here there are calculation of maximum of such function as function of alpha leads similar results. And as you can see, at low alpha we have quadratic behavior, and at high alpha we have linear behavior. But in the case of fractional term, we have approximately linear behavior. And here also some fundamental moments related with superconducting qubits, and here about Shor algorithm, which is the beginning of quantum computing. Last year's this one, as shown by Shor, in the using quantum Fourier methods shows that exponential problems can be converted to normal polynomial problems, and development of technology leads to realization of qubits and quantum calculations. And here also simple, maybe for young people, for pedagogical. You're right. I use yes, yeah. This one here, this one my fault. You are right, Brian. Here classical systems and here quantum systems, and changing of state of one of qubits leads to changing of over to quantum systems, and this leads to quantum parallelism, and as a result to the results related with quantum computation. Quantum computation and entangled state, this one, it is possible the state of in quantum mechanics, if take two qubits, in this case we have no entangled state, so we have such equation alpha delta and beta gamma is 0. It means that in this case we have factorization, and wave function can be presented as production of two wave function. And if no factorization, it means that entangled state was discovered many years ago by Schrödinger, but only last years pupils, researchers would like to apply in also this your this one here, as you can see, also two qubit state and Bell state, and here also Einstein-Podolsky state. This state is states with maximum entanglement state. And here I present also a schematic of quantum computing in the case. As you can see, quantum computing is this one quantum mechanical system embedded to classical environment, and here we use algorithms, this one unitary transformations of wave functions of qubits, and the result can be measured, and as a result we can find a solution of the problem. And here also I present possible qubits, and there are microscopic and macroscopic. In our case, we study this one charge energy and Josephson energy, and ratio of these two energy is the important parameter in study of dynamics, because of, in the case, if we have Coulomb energy is higher than Josephson energy, here we have charge behavior, and inside small Josephson junctions, it is possible Coulomb blockade and related phenomena, and using here Josephson junction and gate and here Island, we can tuning voltage on Josephson junction, and changing of number of Cooper pairs leads to results similar to and in opposite case, when we have two limits, and in these limits Josephson energy is higher than here, we have a phase as sensitive parameter, and as a result we, and also here as you can see here, changing of this ratio, and this ratio is proportional, we can calculate this one is proportional to A in square. A is the junction area. In the junction area, and here last year's pupils in different laboratories realized different types of Josephson qubits, superconducting qubits. And here I present my main aim of our study is the calculation of plasma frequency in anharmonic Josephson junction. Anharmonic, it means in current phase relation we have, because here we have classical harmonic oscillator spectrum, and here as you can see omega plasma is plasma frequency also can be calculated using of our effective critical currents, effective critical currents. Well, yeah. The same problem, yeah? Allah. Yeah, no problem. This one. Yine çalışmadı. Ne oldu? Ne oldu? This, yes. And in the case of current phase relation in which we have a second term, anharmonic term, I show changing of plasma frequency. As you know, plasma frequency is proportional, is square of effective critical current, and effective critical current calculated in the case of sinus phi and alpha sinus 2 phi. And in the case of single band, two band superconductors, many band superconductors, then here we have a changing also this one plasma frequency. In the case of pi Josephson junction, it means that in this case we have synfas supercurrents, and in this case we opposite direction Josephson currents. And in similar way, I would like to show changing of plasma frequency in the case of three-band superconductors, and here IC3 over IC1, and here a changing of character of, as you can see here, we have this one, first one, this one, second one, and in this case we have a result which is similar to two-band case. And in similar way, this one, the study of phase qubits. In phase qubits, we use only single Josephson junction, but in the case of flux qubits, we have superconductor ring with Josephson junction. If we take Josephson junction with anharmonic current phase relation and maybe a single band, multi-band superconductor, in this case, changing also characteristics should be taken into account. And here also general expression for potential energy. And here I show plasma frequency in flux qubit with anharmonic character of Josephson junction. As you can see here, we have a picture similar to if L is 100. In this case, we have this one quadratic behavior, and here we linear behavior, and this one similar behavior of single Josephson junction, and changing of inductance of AC squid. In this case, presented in this picture, and changing of this one, changing of plasma frequency will lead to changing energy difference between states 0 and 1. And also here I present results related in the case of also single band, two band superconductors. As you can see in this case, we have a single junction behavior, as you can see, and changing of character of plasma frequency in the different inductance parameter also presented in this picture. And here also present the result of flux qubit in the case of single band, three band superconductors, and changing also plasma frequency in different cases. As you can see here, we have behavior related with the case in the case of single Josephson junction, but in the case of low inductance AC squid, we have behavior also similar to this one, but there are total increasing of frequency, and here also we have similar pictures. And here also I would like to say any words related with silent qubits due to exclude external fluctuation related with applying of the external magnetic flux. In the case of second harmonic in current phase relation, it is possible take such, for example, potential of Josephson junction, and in this case we have as shown in this study, we can creating of silent qubits. Silent qubit, it means without any external magnetic field, and in this case, due to absence of external magnetic field, coherence time should be better. And here also similar calculation was conducted in our study, maybe many years ago. And here, as you can see, Mathieu pictures, and in these pictures we take into account inclusion of second term leads to changing of energy spectrum of total system, and here result of our calculations. But this one generally our calculations, but last year calculations I show few minutes ago. Here changing of delta 0, delta 1, this one first band and second band using Mathieu equations with anharmonic current phase relation. And here I would like finish my presentation, and basic equation of Josephson dynamics is presented. Maybe is useful for young people, and other parameters, symmetry and multiple character of new superconducting materials should be taken into account in calculation. For example, energy difference of in Josephson junction qubits, in phase qubits, and in flux qubits, and influence of this characteristic, this methods taken into account with calculation of effective critical current of Josephson junction in the case of anharmonic current phase relation, and in the case of frustration effects in multiband superconductors. Yes, thank you.
Okay, thank you for the talk. I appreciated having seen 5 slides from my lectures. Anyway, they're useful for community. Questions, please.
Thank you for a nice talk. So I have a question. So basically you are using the concept of washboard potential, but without fully, justified derivation from BCS theory. So do you see, actually I'm author of the paper about the derivation of washboard potential from BCS theory. So I would say, do you see any attempts to be more fundamental from the prescription of Josephson effect? Because this is like reverse engineering. We have a washboard potential that is fulfilling the equations of motion, but actually like a BCS theory creates a more effective washboard potential that can be later approximated to the washboard potential that we are using. So can you make any comments on that?
Yeah, you are right. In principle, here is more a complicated form of current phase relation, but in general case I show in the first slides, there are very simple equation, beta Macamber parameter and second derivative of phase, and this first derivative and science phi. We have 3 components, and we use resistive shunted Josephson junction model because of.
This is not a fundamental model.
Yeah.
This is absolutely phenomenological.
Yeah, you are right. For study of here, as you can see here, we generally in books, in calculations, in superconducting electrons, people using this equation. This one, if you take unitless case of this parameter, this one is proportional to Macamber parameter, and this one resistive term, and this one Josephson term. And mainly people use this variant because of, you are right, because of sometimes this relationship in tunnel junctions, yeah, you are right. In tunnel junctions, this sinus phi seems more very simple and very, very simple. But in order to obtain results, we need in such analytical models and in such analytical equations, because of there are, for example, in Bogoliov-Dejean equations, using Bogoliov-Dejean equations, we cannot get to simple science phi Josephson current. Here we have a more complicated expression. But in our studies, for example, in our calculations, it is enough.
Any further questions, please?
You have shown then some expression for current where doubling of the phase difference occurs,
Yes.
or frequency doubling. I don't know. So where from does it come? I mean, what is the reason? No, frequency doubling, phase doubling, sine phi plus sine 2 phi.
Yeah. Yes, this one.
Where from? What is the reason for such?
As I understand, for example, in the first paper by Sigrid Streiss, in the first calculation, taking into account D-wave character of symmetry of order parameter in left-right superconductors, leads to this result, science phi. But here we have quotient 2 phi, theta le, and theta re, and inclusion this term related with taking into account D-wave character. And from another point of view, here, as you can see, experimental results. This equation. Here also we introduce sometimes maybe phenomenologically because of the, but here there are experimental results which show that at low temperature, second term becomes more important and should be taken into account of study qubits on-site Josephson junctions. This Josephson junction on IPCO grain boundary Josephson junctions, and yes.
I would have a question where actually, what kind of materials do you consider? Because so far there would be no qubits made of high TC YBCO junctions. And the reason is that they are having very high loss. So the qubits require small dissipation. And once you take exotic materials like this, or two-band superconductors, then the losses are much larger than in tunnel junctions, conventional tunnel junctions, and the qubits don't work. So I wonder which particular materials, except for YBCO, did you consider here?
This one here generally is developed any model for the study, for example, in the case of, from the academical point of view, inclusion of second term, how will influence of to, for example, say energy distance between zero level and phase level, because of this one very important in the case of control parameters of qubits. And in the case of multiband superconductors also we have introduced any similar terms, and there are another authors also takes such approach, and using such simple models, sometimes it is possible to get useful results. It seems sometimes for the experimentalists, but from the point, you are right, from the point, general point of view, in the case of qubits, there are special moments should be taken into account. Yeah.
Okay, thank you. Any further questions? Okay, let's thank the speaker again. And I'm honored to give you the certificate. Okay, thanks. Do we have the last speaker of the session?
Tamam. Ya, tamam.
Okay? Okay. So the last speaker